We're now going to talk about some other interfaces that are used in conjunction with the executor service. And you typically need to be aware of these things in order to understand the programming model and how it can be applied in practice. And those other interfaces will be Runnable, which you already know, Callable, which I've mentioned in passing, but you'll get a bit deeper understanding now, and Future, which I've also mentioned, but you probably don't know in detail yet. So these three interfaces, Runnable, Callable, and Future, are used by the executor service to manage the life cycle of tasks. There are two interfaces the executor service uses to define tasks, Runnable and Callable. As we talked about before, in the context of the executor interface, Runnable is an interface that provides a one-way task that does not return a result directly. If you want any results, they have to come through side effects. And it's a functional interface, meaning there's just one abstract method in it. Callable is a two-way task that returns a result, and the result is of type V. So you can see Runnable has no return value from run, whereas Callable actually returns something of type V. It's also a functional interface for that matter. The main important difference is that a Callable is a two-way task that returns a result. So that means you can get a result back, and that has some nice properties we'll take advantage of when we redo the implementation of our Prime Checker app shortly. You typically use Callable to run two-way asynchronous tasks. So let's just briefly talk about different kinds of tasks. One is a one-way asynchronous task, which we sometimes refer to as fire and forget. You fire it off and you don't really care if you get a result back. That's kind of like mailing a letter. You put it in the post box and maybe you get something back, maybe you don't. You could also do two-way async tasks. So that would be kind of like mailing a letter with some kind of receipt acknowledgement. You send out something and the person who gets the letter has to sign for it, and then you get the acknowledgement that the letter was received. So that would be an example of a two-way task where you get something back. However, if you think about it, that's asynchronous. When you drop off a letter to be mailed to the person who's going to sign for it, you don't sit by the mailbox or by your mailbox at your house waiting for the response. Those things take place asynchronously. Much like sending email, right? You send an email, you can also have sort of the return received thing set up there so that you know if someone read the mail or not. In contrast, placing a phone call where you talk to someone is a synchronous two-way task, because you call somebody and you wait for them to answer, and then you have this conversation, and you do that synchronously. You're talking to them back and forth without waiting. You may wait for them to pick up the phone. You may wait for them to respond to your questions, but you're having a conversation, a dialogue. The executor service implements a variant of the active object pattern. And the active object pattern is a pattern that appears in the Posted To book. I was the lead author for that book. You can also read about it on Wikipedia. And basically, the active object pattern decouples the thread that invokes a method from the thread that executes the method. And there's a bit more things it does too, but that's one piece of it. So you can see here that the client invokes an operation, typically by making a method call. That turns into some kind of message that's passed over to the active object. The active object will insert that message into a queue, and it'll have a scheduler that schedules the next execution, and that typically ends up calling a method back in the implementation of the active object, and it does something, and it can either do one-way or two-way things. In this case, it does two-way things. Results can be provided back via something called a future. We'll talk about future in a second. The future is an interface that's used by the executor service to represent and control the life cycle of a task. So you can think of a future as a proxy that some other thread can use to represent and control the result of an asynchronous computation. So this is from a book I also co-authored. This is the Pattern-Oriented Software Architecture Volume 4 book, and this is a diagram from that. This shows the interactions between the different key parts of a future. So some client thread invokes an operation, and then it can go ahead and use the future to get the result. And the way that works is if the result is not immediately available, we wait for the result, and then when the result is finished, the result is provided and it's returned to the client. So this computation runs asynchronously in some background thread, and the result is obtained only after the computation completes. There's a lot more to futures. We'll talk about them. That's basically the gist of it, though. It's a proxy that represents and controls the result of an asynchronous computation. Well, as you know, I love human-known examples of everything. So this is my example. Table tent numbers or their paper equivalents are good examples of human-known uses of futures. And let's see if we can talk about this. So back in the day, there were sort of two models for going to a fast food restaurant. One model was the McDonald's model, where you would go in and there'd be a line of people and a couple of cash registers, and McDonald's would pre-cook a bunch of food, hamburgers, French fries. They would pre-pour the drinks. And when you came up to the cashier, you'd say, I want a Big Mac, large fries, and a Diet Coke, or whatever you wanted. The cashier, the server would say, that sounds good, give me your money. You'd give them the money. The cashier would turn around, grab the pre-cooked Big Mac, the pre-cooked French fries, and the pre-poured Coke, give it back to you, you're on your way. The problem with that model, by the way, that's a good example of caching, right? So we pre-cache the food in advance of its being used. The problem with that is if the food sits out for a while, it gets kind of old, right? Who wants to eat French fries that have been sitting around in the heat lamp for 12 hours? Nobody. So it's not very fresh. So Wendy's came along and they had a different model. They said, hey, we're going to cook your food to order. Every hamburger will be made specially for you. So you go up, you order your whatever Wendy's has. It's not a Big Mac. It's probably a Dave Thomas burger or something like that, because he was the founder. And so you order your burger, you pay for your food, and rather than standing there at the cash register waiting to get your order, they give you a table tent number. Back in the day, it would be like a number like this on a piece of plastic. Nowadays, it's probably a receipt with a number on it. And then you would go off and you would, check your phone or read the newspaper or talk to your friends or text your friends or whatever you're doing while your food is being cooked asynchronously by the cooks. And then when your food is ready, you have sort of two ways to get it. You can either go back up after some period of time and say, hey, is order number 12 ready? That's called the polling model. And if it is, they'll give you your food and take your number. If it's not ready, you can either stand there and wait for it to be ready, or you can go back and talk to your friends, text your friends, pour yourself a drink, whatever you need to do, and then go back and check again. So those are one way. That's the polling model with timeouts and blocking. And the other model is the callback model, where you sit there with your table tent number, and when your food's ready, they bring it out to you and drop it off. And you actually see that a lot if you go to various kinds of delis, like McAllister's or Jason's Deli. You order your food, they give you a table tent number, you put it on a big pole, and then they bring the food to you later. That's the callback model. So those are ways of redeeming your order. And the whole reason why they did it that way was because the key bottleneck in the fast food restaurant is the cash register. You want to get as many people through that as possible as quickly as you can, because that generates revenue. So if they're going to cook your food to order, they don't want you standing there blocking all the other people who want to be serviced, because you want them to go in there and place their orders and go sit down. So it's all about throughput. So the way to think about this is the McDonald's model is based on caching, and that's how they do throughput. They have a rendezvous synchronous model where you pay and get your food and wait, whereas this is an asynchronous model. The Wendy's model is a fundamentally asynchronous model. And futures are a means of communicating from the preparer of the food to the consumer of the food that you have got your order when it's ready. Okay, popping out of human known use metaphor land, programs use futures to represent and control a task lifecycle via five methods. Cancel, is canceled, is done, get, and get. There are two versions of get. One is timed, one is blocking. So one way you can do things is you can start the computation running, and then you do your thing, whatever you do. Your program does whatever the equivalent of checking your email, texting your friend, drinking your soda, reading a newspaper. That's what your program is doing. And then when it finally gets to the point where it says, I want to eat, darn it, I'm going to block now, you can call get. And there's a couple different variants. You can call the timed version, which says I will wait for up to this amount of time, and if I don't get my stuff, I'll do something else. Or you have the blocking version. This is the blocking version here. It just says wait until this thing is done. You can also check to see if the computation is done. So you can say, hey, is it done? If so, I'll call get. And then there's a couple of other methods to deal with cancellation. You can see if you've been canceled, like you decided you didn't want to wait for your hamburger anymore, so you go ask for a refund. And then you can also cancel your order. You can say, I don't want my hamburger anymore, give me my money back. So there's a couple other things you can do. These are all things you can do on a future as a thread that's trying to get the results of an asynchronous computation. Now, how do you submit this thing in the first place? Well, funny you ask. It's called submit. There's a method that's part of ExecutorService called submit that can initiate an asynchronous computation in Java. And as you can see here, we can make ourselves a fixed thread pool. We could also do other kind of thread pools, but let's make a fixed one. We can then go ahead and make ourselves a task. This particular task is a callable that will multiply two big fractions together and return the result. And then we can go ahead and we can submit that task into the ExecutorService. So we submit the task. And that will then return a future, which we'll talk about later. It's implemented by something called a FutureTask, which we'll discuss in an upcoming lesson. And then the asynchronous computation that we requested here, that we submitted here, runs in the background. We do our thing, whatever we do. And then at some point, we decide we want to wait for the result. Now, keep in mind, if you submit an asynchronous computation and immediately sit there in a get call blocking, you've totally defeated the whole purpose of futures and asynchrony, because you might as well have just done a synchronous computation for all it's worth, because you're getting no benefit of concurrency. You're getting overhead of concurrency. So at some point, we call get, and that can either block or timed pull, and we get the result back, or we get back the error that occurred if things didn't succeed, if they completed unsuccessfully. Now, one of the things to note about this asynchronous model is that results can occur in a different order than the original calls were made. So you could submit something, you can submit something else, you might get a result from the first submission, you can submit something else, you get the results from that one, and then finally get the results from this one. That's the beauty of asynchronous computation. You don't know, you don't care about the order in which things run. So longer running jobs may take longer, shorter running jobs may take shorter. You get the results back when the results are done. Futures are also applied in the context of the active object pattern that we talked about before. So what you do there is a client initiates a computation that runs in the thread pool, and then it gets a future right away, and at some point the client can use the future to get the result of the asynchronous computation when it completes. There are other variants of futures that are implemented by the ExecutorService. For example, there's something called a Runnable future, which extends Runnable and future. So it's a Runnable future. We'll talk about that later. There's also something called a FutureTask, which is a really cool class that conveys the results from a thread running a task to threads that are retrieving the results. And then there's also something called a completable future. We will not cover completable future in this course. This is a very, very powerful extension of future that supports dependent actions triggered upon the completion of asynchronous operations. This is what's covered in my sibling course, which is the parallel functional programming course, which some of you have taken. So you've got a chance to play around with this stuff. Interestingly enough, completable future really is not part of the executor framework at all. It's a totally separate thing. It's a really, really cool thing. But like I said, that's not part of the object-oriented aspects of concurrency in Java. That's part of the functional parallel processing and asynchronous processing part. So we won't cover it here, but we'll cover it in my other class. The ExecutorService also forms the basis for key Java executor framework subclasses. And we'll talk about these things later. So you'll see how there's other things like abstract executor service and thread pool executor and fork join pool and scheduled thread pool executor, which will be topics in future lessons. So that's the end of our discussion of related interfaces that are all part of the ExecutorService portion, the ExecutorService interface portion of the Java executor framework.